A satellite navigation or SatNav system is a system of satellites that provide autonomous geospatial positioning with global coverage. It allows small electronic receivers to determine their location to high precision using time signals transmitted along a line of sight by radio from satellites. The signals also allow the electronic receivers to calculate the current local time to high precision, which allows time synchronization. A satellite navigation system with global coverage may be termed a global navigation satellite system. As of April 2013, only the United States NAVSTAR Global Positioning System and the Russian GLONASS are global operational GNSSs. China is in the process of expanding its regional Beidou navigation satellite system into the Global Compass navigation system by 2020. The European Union's Galileo is a GNSS in initial deployment phase, scheduled to be fully operational by 2020 at the earliest. France and Japan are in the process of developing regional navigation systems. Global coverage for each system is generally achieved by a satellite constellation of 20 to 30 medium Earth orbits satellites spread between several orbital planes. The actual systems vary, but use orbital inclinations of greater than 50 degrees and orbital periods of roughly 12 hours. Classification. Satellite navigation systems that provide enhanced accuracy and integrity monitoring usable for civil navigation are classified as follows. GNSS-1 is the first-generation system and is the combination of existing satellite navigation systems with satellite-based augmentation systems or ground-based augmentation systems. In the United States, the satellite-based component is the Wide Area Augmentation System. In Europe it is the European Geostationary Navigation Overlay Service, and in Japan it is the Multifunctional Satellite Augmentation System. Ground-based augmentation is provided by systems like the Local Area Augmentation System. GNSS-2 is the second generation of systems that independently provides a full civilian satellite navigation system, exemplified by the European Galileo positioning system. These systems will provide the accuracy and integrity monitoring necessary for civil navigation, including aircraft. This system consists of L1 and L2 frequencies for civil use and L5 for system integrity. Development is also in progress to provide GPS with civil use L2 and L5 frequencies, making it a GNSS-2 system. Core satellite navigation systems, currently GPS, GLONASS, Galileo and Compass. Global satellite-based augmentation systems such as OmniStar and Starfire. Regional SBAS including WAS, EGNOS, MSAS and GAGAN. Regional satellite navigation systems such as China's Beidou, India's yet-to-be operational IRNSS, and Japan's proposed QZSS. Continental-scale ground-based augmentation systems, for example the Australian GRA and the U.S. Department of Transportation National Differential GPS Service. Regional-scale GBAS such as CORS networks. Local GBAS typified by a single GPS reference station operating real-time kinematic corrections. History and theory. Early predecessors were the ground-based Decca, LORAN, G and Omega radio navigation systems, which used terrestrial long-wave radio transmitters instead of satellites. These positioning systems broadcast a radio pulse from a known master location, followed by a pulse repeated from a number of slave stations. The delay between the reception of the master signal and the slave signals allowed the receiver to deduce the distance to each of the slaves, providing a fix. The first satellite navigation system was Transit, a system deployed by the U.S. military in the 1960s. Transit's operation was based on the Doppler effect. The satellites traveled on well-known paths and broadcast their signals on a well-known frequency. The received frequency will differ slightly from the broadcast frequency because of the movement of the satellite with respect to the receiver. By monitoring this frequency shift over a short time interval, the receiver can determine its location to one side or the other of the satellite. And several such measurements, combined with a precise knowledge of the satellite's orbit, can fix a particular position. Part of an orbiting satellite's broadcast included its precise orbital data. In order to ensure accuracy, the U.S. Naval Observatory continuously observed the precise orbits of these satellites. As a satellite's orbit deviated, the USNO would send the updated information to the satellite. Subsequent broadcasts from an updated satellite would contain the most recent accurate information about its orbit. Modern systems are more direct. The satellite broadcasts a signal that contains orbital data and the precise time the signal was transmitted. The orbital data is transmitted in a data message that is superimposed on a code that serves as a timing reference. The satellite uses an atomic clock to maintain synchronization of all the satellites in the constellation. The receiver compares the time of broadcast encoded in the transmission of 3 or 4 different satellites, thereby measuring the time of flight to each satellite. Several such measurements can be made at the same time to different satellites, allowing a continual fix to be generated in real time using an adapted version of trilateration. See GNSS positioning calculation for details. Each distance measurement, regardless of the system being used, places the receiver on a spherical shell at the measured distance from the broadcaster. By taking several such measurements and then looking for a point where they meet, a fix is generated. However, in the case of fast-moving receivers, the position of the signal moves as signals are received from several satellites. In addition, the radio signals slow slightly as they pass through the ionosphere, and this slowing varies with the receiver's angle to the satellite. Because that changes the distance through the ionosphere, the basic computation thus attempts to find the shortest directed line tangent to 4 oblate spherical shells centered on 4 satellites. Satellite navigation receivers reduce errors by using combinations of signals from multiple satellites and multiple correlators, and then using techniques such as Kalman filtering to combine the noisy, partial, and constantly changing data into a single estimate for position, time, and velocity. Civil and military uses. The original motivation for satellite navigation was for military applications. Satellite navigation allows for hitherto impossible precision in the delivery of weapons to targets, greatly increasing their lethality whilst reducing inadvertent casualties from misdirected weapons. Satellite navigation also allows forces to be directed and to locate themselves more easily, reducing the fog of war. The ability to supply satellite navigation signals is also the ability to deny their availability. The operator of a satellite navigation system potentially has the ability to degrade or eliminate satellite navigation services over any territory it desires. Global satellite navigation systems. Operational GPS. The United States' global positioning system consists of up to 32 medium Earth orbit satellites in 6 different orbital planes, with the exact number of satellites varying as older satellites are retired and replaced. Operational since 1978 and globally available since 1994, GPS is currently the world's most utilized satellite navigation system. GLONASS. The formerly Soviet, and now Russian, Globalnaya Navigationная Sputnikovaya Sistema, or GLONASS, was a fully functional navigation constellation in 1995. After the collapse of the Soviet Union, it fell into disrepair, leading to gaps in coverage and only partial availability. It was recovered and fully restored in 2011. Doris Doppler orbitography and radio positioning integrated by satellite is a French precision navigation system. However, unlike other GNSS systems, it is based on static emitting stations around the world, the receivers being on satellites. In order to precisely determine their orbital position, Used with traditional GNSS systems, it pushes the accuracy of positions to centimetric precision, in order to build a much more precise geodesic reference system. In development, Galileo, the European Union and European Space Agency agreed in March 2002 to introduce their own alternative to GPS, called the Galileo Positioning System. At an estimated cost of €3 billion, the system of 30 MEO satellites was originally scheduled to be operational in 2010. The original year to become operational was 2014. The first experimental satellite was launched on 28 December 2005. Galileo is expected to be compatible with the modernized GPS system. The receivers will be able to combine the signals from both Galileo and GPS satellites to greatly increase the accuracy. Galileo is now not expected to be in full service until 2020 at the earliest and at a substantially higher cost. Beidou China has indicated they plan to complete the entire second-generation Beidou navigation satellite system by expanding current regional service into global coverage by 2020. The BEIDOU-2 system is proposed to consist of 30 MEO satellites and 5 geostationary satellites. A 16-satellite regional version was completed by December 2012. Comparison of systems. Regional satellite navigation systems. BEIDOU-1 Chinese regional network to be expanded into the whole global system, which consists of all 35 satellites by 2020. IRNSS. The Indian Regional Navigational Satellite System is an autonomous regional satellite navigation system being developed by Indian Space Research Organisation, which would be under the total control of Indian government. The government approved the project in May 2006, with the intention of the system to be completed and implemented by 2015. It will consist of a constellation of 7 navigational satellites. All the 7 satellites will be placed in the geostationary orbit to have a larger signal footprint and lower number of satellites to map the region. It is intended to provide an all-weather absolute position accuracy of better than 7.6 meters throughout India and within a region extending approximately 1,500 kilometers around it. A goal of complete Indian control has been stated, with the space segment, ground segment and user receivers all being built in India. The first 4 satellites IRNSS-1A, IRNSS-1B, IRNSS-1C and IRNSS-1D of the proposed constellation were precisely launched on 1 July 2013. The 4th of April 2014, the 16th of October 2014 and the 28th of March 2015 respectively from Satish Dhawan Space Center. Of the remaining 3 satellites, IRNSS-1E has a planned launch in November 2015. IRNSS-YF has a planned launch in December 2015 and IRNSS-1G should be in orbit by March 2016. QZSS. The Quasi-Zenith Satellite System is a proposed 3-satellite regional time transfer system and enhancement for GPS covering Japan. The first demonstration satellite was launched in September 2010. Augmentation. Examples of augmentation systems include the Wide Area Augmentation System, the European Geostationary Navigation Overlay Service, the Multifunctional Satellite Augmentation System, Differential GPS, and Inertial Navigation Systems. Low Earth Orbit Satellite Phone Networks. The 2 current operational low Earth orbit satellite phone networks are able to track transceiver units with accuracy of a few kilometers using Doppler shift calculations from the satellite. The coordinates are sent back to the transceiver unit where they can be read using at commands or a graphical user interface. This can also be used by the gateway to enforce restrictions on geographically bound calling plans. Positioning calculation.